it means this terminal voltage is also increasing. I'm going to write it down, don't worry. And now, as you see, we have increased voltage on both terminals of the first amplifier. It means the difference between, let me name this one V4. It means the difference between V1 and V4 is either kept constant or it's decreasing. And that shows that we're working on a negative feedback amplifier. It means the output is controlling the difference on the voltage of input, the input voltage of the terminal positive and terminal negative of A1. So let me write it down. So if the S increase, then we know that V1 is increased. If V1 increase, then V2 is decreasing. So from here. If V2 decrease, V3 is increasing. If V3 increase, then the output is also increasing. Then since a part, since a part of output voltage is getting back to input positive terminal, and then V4 on the positive terminal of A1 is also increasing. Okay, then this is also increasing. And what is the result? It means the difference. So finally, the difference between V1 and V4 is either kept constant or it's decreasing, which verifies the negative feedback. Remember, negative feedback always controls the input, controls the input voltage on the input voltage difference on the negative and positive terminal of an amplifier. Okay. So far, we're good. Let's move on to part B. Guys, in part B, we should work on, it says if R1 is 20 kilo ohm, find the value of R2 that results in a closed loop gain of 5 volt per volt. So it's like R1 is given, R1 is assumed to be 20K. It is asking us to find R2. So for this means, okay, I would simply say that part B. I would simply say that our amplifier, an ideal amplifier, feedback gain is assumed to be 5 volt per volt. And on the other hand, I know that AF is 1 per beta. Okay. Now let's look at this. Let's look at this given configuration. Before, you see 1/beta should be 5, then out of here, beta is assumed to be 0.2. So beta on your feedback is assumed to be 0.2. Now, how can I design R2 such that the beta will remain 0.2? You know that beta goes back to your feedback. If you want to write down beta on the given feedback loop here, you see this guy I'm talking about? This I'm talking about. So if you want to find beta here, beta is the feedback loop gain. So what is it? You would say that beta is the voltage over is like the division between R1 and R2. So it will be R1 over R1 plus R2, because R1 and R2 will be in series connection, and R1 as like is connected to R1. Let's say is a voltage can be assumed like the voltage connected to positive terminal at A1. So then out of here, this should be equal to 0.2, while R1 is given by 20k ohm and R2 is missing. So if you just do some simple simplifying, R2 will become 80 kilo ohm. So this is our second step. Feedback gain was given, we found beta, and out of beta we found one of the missing resistance on our feedback loop. So now let's move on to part C. In part C, it says supply the small signal equivalent circuit. You know that we have a small signal circuit for each of the amplifier. It means if you replace each amplifier with an equivalent circuit, and then you will end up having a newly formed amplifier, and in that newly formed amplifier, actually after breaking up the feedback loop, then you are going to have your small signal equivalent. So let me show it here. I can say that since I don't have it on a large screen, I can scroll up very much, but I try my best. So let's replace every amplifier with an input resistance, a gain, and output resistance. So in the beginning, I have the same positive and negative Vs. Then Rs is still there. This is an Rs. And the input of A1, I'm going to put the input resistance. So input resistance of A1, imagine that it's, by the way, the question gave us all this information. Input resistance of A1 is 82 kilo ohm. And this is positive and negative of, I'm going to name it V1. What is V1? V1 is the voltage difference here. Voltage difference over the input terminals of A1. Now, this will be, as you see, this will come down and then be connected to, will be also connected to the feedback loop. So I'm not gonna show it with the same color. I'm gonna go back and show it with this color, like it is connected to our R1, which was 20k. Now, what we have on the other side? Now you should show the gain of A1. And the question says open circuit voltage gain of A1 is 20 volt. So it means we have a voltage source, which is 20 times of the voltage on the left side. And now you have an output voltage, and our output voltage is given by 3.2. So this is all about A1. Now, this from here, it is connected to A2. And the input resistance of A2 is 5 kilo ohm. So finding it positive negative V2, this is 5K. And then you have, what was it given? It was, you have a short circuit transconductance on the other side. So the short circuit transconductance on the other side means that we're not going to have a voltage source. We're going to have a current source on the other end. And that is 20. The question says that the transconductance voltage current source is 20 milliamp amp over volt. So it's like it is 20 times of V1. So, sorry, 20 times of V2. And now you have your output resistance, but your output resistance will be also connected in parallel, which is 20K. Now from here, this is going to be connected to A3, and A3 has an input resistance, which is 20K. I'm going to name this one V3, and here is 20K. It is connected to, let me clean this part, I'm going to write it down later. It is connected to the other end for the gain, and gain is a unity gain. So it means we have V3 over here, and now you have your output resistance, which is 1 kilo ohm. And then you have your load on, and then that's it. So on the other end, you will have the V output, and you will have the load here, RL. But listen, what about the feedback loop? The feedback loop will be connected from here all the way up to here, like this, and this is R2. So we found R2 to be 80K, R1 to be 20K. This is a small signal equivalence. I have not broken the feedback loop yet, but I will do it in other steps. This is our small circuit equivalence. Small circuit equivalence. Okay. Now, after this, let's move on to part D of the question. And by the way, if I want to be more accurate, this is related to A1, this is related to A2, and this part is related to A3. You can also show it with things like this. You have it in your textbook. And from here on, something like this. Okay. Now let's move on to part D. Guys, in part D, it says sketch the A circuit and determine A. Okay. What is an A circuit? A circuit, remember this. I know that many students during the final exam is going to ask, what is A circuit? A circuit means break feedback loop and form a newly formed amplifier. Remember this word, newly formed amplifier. It means this happens after breaking the feedback. So now let me go ahead and break this feedback. If you want to break the feedback, you have to consider the effect of feedback both on the input side and on the output side. So what do we have on the input side? By the way, so far, I just forgot to show it to you. If I want to show I would say, so okay, that's fine. So if I want to break the feedback, it's like I have an eye here and I'm looking at this feedback. So while you are looking at it, you're gonna assume that on the other end, on the right side, you will have a short circuit. So if you have a short circuit, then when you're looking from here, you're looking at R11. R11 will become R1 connected to the ground, and if V also connects to the ground, so it means R1 and R2 are parallel together. So this means R1 and R2 are parallel. Now, if I'm going to break this loop, I have to consider the effects here as well. From here, I'm seeing R22. So what is R22? When you're looking from this, imagine that you have your eye here and just looking at it. In this case, we only assume that there is no current passing through this loop anymore. It means there is no current passing through here, I equals 0. If that I equals 0 and you're looking at from here, it means that R2 and R1 are in one series connection, right? So I would say R22 will become R1 plus R2. So R1 plus R2 is 80 plus 20, which is 100K. R1 parallel to R2, like 20 parallel to 80, is 160K. Now, I'm going to break the loop. I'm going to form a newly formed amplifier, and just going to draw the circuit one more time. So that our newly formed amplifier will become the same thing, just I'm going to break the loop. So it will be something like VS, we have RS, we will have 82K, and in the following, I'm going to have R11, so R11 will show up here as it is connected to 82K along. And here I'm going to have the same voltage gain. It is 3.2K. Then I have 5K. 22. 20K, another 20K, and here is positive negative V3. And on the other hand, we have a voltage gain, unity voltage gain, output resistance, which is 1K. Then you have your R22, and then you will have your R load, which is connected to output voltage. R load. Okay, that's it. Fine. Now, if after breaking your after breaking your feedback, something will happen to your input resistance and output resistance. Previously, if we were here, if you looked at here, we were looking at Rn, and if we were looking at from here, we were looking at Rout. Now, it is still the same. You would say that you're still looking at Rout from here, and Rin from here. But if you want to consider the effects of that Rs and R load, then you are going to have your ROF and this is going to be a feedback output resistance, and this is going to be RIF. Remember this. So Rout is different from the feedback output resistance. Now let's continue this. Wow, it's a long question. By the way, this is I think in part D. In part D, and then in part D, the question was asking also about the gain. After forming the amplifier, it was asking about the gain. How can I find the gain here? So let's see how can I do this. First of all, I know that you can. That's okay to call that. It's okay. So if we want to find our if I want to find the voltage gain, I'm gonna form the A as like a chain rule. I would say VO versus VO versus V3, V3 versus V2, V2 versus V1, V1 versus VS, and that's it. So I don't need this different properties. VO versus V3, V3 versus V2, V2 over V1, V1 over Vs. So let's find this one by one. First of all, let's go for finding V1 versus Vs. Remember, Rs is given by 9K, and RL was also, I think, 1 for all. That's fine for now. So let's find V1 versus Vs. Guys, V1 versus Vs, we are only in the first 1/4 of the total circuit. V1 is the voltage over 82 kilo ohm. So it's like you have 82 kilo ohm divided by, now Vs is over Rs, 82 kilo ohm, and R11. So you will have 82, 9 kilo ohm, and R11, which we found it to be 16. Okay. Now, if you do if you calculate here, you will have 0.766 volt per volt. Let me just check if I'm right with the direction things. Okay. Oh, look at here, guys. Sorry, I forgot something. This is, you see the amplifier over here? A has the opposite. Or sorry, that's the other end. I would say V1 is the opposite of opposite in terminal compared to Vs. So it's like this. If V1 and Vs have opposite directional terminals, then in your, it means here is negative, here is positive. It means here you will also include a negative. Now you're fine. So now our next job is to find V2 versus V2 over V1. So for finding V2 over V1, I have to work here, right? So I would say, what is V2? V2 is the voltage over that 5K, and while we have another voltage source of 20 V1 over there. So it's like you are writing a KVL in this loop. That's pretty easy. And I'm not going to write down the KVL, I'm just going to tell you how to do the voltage division. It's like I'm doing a voltage division between 5K and 3.2K, so it will be 5K over 5K plus 3.2K times the total voltage in this loop. And the total voltage in this loop is 20 V1. By the way, by doing this, you're finding V2, right? Because I want to find V2 over V1, I will drag this V1 down here, and I will clean it from this way. See? So now this is going to be your V2 over V1. She will end up having 12.19 volt per volt. Now our next job is to find V3 over V2. So we have V3 over V2. For V3 over V2, you have to work here. V3 is a voltage over 2 parallel to a 2K resistance, while the current of 20 V2 is passing through them. That makes sense? It's like now that 20 V2 is which is actually going to be 20K parallel with another 20K, while 20 V2 is passing through it. I'm not going to write that 20 V2 here. Oh, let me write that. Then negative 20 V2 is passing through it. Again, if you do some rearrangements, if you cancel out V2 from here and divide both sides of the equation by V2, V3 over V2 will be negative 200. And then the last part, for finding VO over V3, you have to work here. Then your VO versus V3 is going to be, Okay, look at it. VO is the voltage over R22 and RL. And then there is a voltage division between the RL and R22 being parallel, and then series with 1K. So finally, I would say R22 parallel RL over that 1K plus R22 parallel with RL. RL, I think, is 1 kilo ohm. R22 we found it is 100, and then finally if you do all the, and by the way, this is times that unity voltage. Unity voltage is 1. So finally you will have 0.497. Then finally altogether for finding A, you have to times everything together. So you will have this times 1219 times negative 200 times 0.497, and your voltage gain will become 928.5 volt per volt. So this is our total A. Remember, A is our voltage gain in a newly formed amplifier. Now that we're done here, let's move on to our next part of the question. So part E, it says find beta and the amount of feedback. Okay, now here from this given newly amplifier, I need to work on finding beta and also the feedback. Remember, beta is always related to feedback loop. So you can look at here one more time for finding beta. Again, beta will be, we found it previously as well, but you see, we found it here as well. I'm just gonna, let's say, repeat it. Beta will be 20 over 20 plus 80, which will end up having 0.2 again. So beta will be 20K over 20K plus 80. We'll have 0.2. So 0.2 volt per volt. And now what is your feedback? Your feedback loop is 1 plus A beta. So it's like 1 plus. We just found A, and here is the value for A. So 1 plus 928.5 times 0.2. So your feedback will become 186.7. This is your feedback. 1 plus A beta. Now let's move on to part F. Sorry, I have to scroll up again. Part F, it says find the closed loop gain. We found A, and A was the open loop gain. Now, if you want to find closed loop gain, you have to use formula. Closed loop gain, and we're talking about AF. And how can you find AF? You have a formula for AF. AF is either VO over VS. You can directly find VO over VS by using the formula. You know that AF, the closed loop gain, has a relation with open loop gain, and it is A over 1 plus A beta. So this is the formula. So then finally plug in the values. Your A value, we just found it, 928.5. 1 plus A beta, we just found it, that's 186.7. Then finally you will have 4.97 volt per volt for your closed loop gain, which is, if you pay attention, it's pretty much close to that 5 volt which we had in the beginning of the question. The question said that consider closed loop gain to be 5 volt. So it's pretty close. What we found is also pretty much the same. Okay, all done with part 5, part F. Let's move on to part G. In part G, you should find the feedback amplifier input resistance Rn.
Okay. As I told you, when you correct this feedback loop, your Rn is right here in this little arrow, the red arrow on the left. And now we should find that Rn. Uh, so for finding Rn, there are some questions, some equations given on. I want to be more accurate about the equation number. I think it's equation. Um, I don't have the accurate equations, but I don't have the equation number, but I have them here. You see this? Ri will be Rid, Rf, and Rs parallel together. Actually, sorry, that goes back to question number 2. In question number 1, for finding your Rn, first you need to find Ri. And that Ri will be 9, 82, and R11's in series connection. So if I add up all these three things, G, I would say our Ri will be 9, 82, and 16 added up together. So you will end up having 107 to go. After you find Ri, you should find your Rif. Ri in closed loop. Remember, Ri in closed loop is always Ri times 1 plus A beta. So it will be 107 times 1 plus A beta is again 186.7. So if you calculate it, you will get 19.98 megaohm. So this is your RIF, but not RN. Look at it, everyone. Our RIF is this orange arrow. You see this guy? Is this orange arrow? Now, how can I find RN? I would say that RIF is like in your RIF, you're also considering that RS. Okay, so if you subtract that RS, then you will end up with this red arrow, which is Rn. So it's like here, if I do for finding Rn, if I subtract RIF and RS, I can find Rn. You see, when RIF is in megaohm and RS is just 9 kiloohm, you will again end up having the same 19.98 megaohm because it's pretty much larger compared to RS. So that's also part G for finding the input resistance of the feedback. Now let's move on to part H. Okay, in part H of the question, you should find the feedback amplifier output resistance. Okay, let's go. For finding the feedback amplifier output resistance. Okay, first of all, let's look at here. First of all, I would say, if you want to find RO, your RO, guys, I'm talking about this part because I'm talking about output resistance. My RO is like you're shutting off that V3 gain, and then RL, R22, and 1K will become parallel together. So RO is like all these three things parallel. RO is like RL, R22, and then 1 kilo ohm in parallel. And if you find it, RO will become, I calculated it here, it's 497.5 ohm. This is RO, this is not your R out. But out of RO, you will always find your ROF. Remember, ROF, let me write it in another color. Your ROF will become RO divided by 1 plus A beta. Okay, now if I substitute the values, RO is 497.5. Guys, we found 1 plus A beta, and it's 186.7. We found it in the previous parts. So finally, your ROF is going to be 2.66. Now let's look at it. Let's go back here and look at it. ROF is here. You do not need ROF. You want R out. But if you pay attention, for fun, ROF is like the load resistance is in parallel with the R out, right? So here it's like ROF is like load resistance is parallel with R out. Okay, give me some seconds. My job is to find R out, right? So you can say that from here, ROF, guys, wait over there, please. What's wrong? Please give me some seconds. Let me finish this. I will get back to the queue and I will answer your questions. So ROF, let's listen. I'm looking for R out. While I found ROF to be 2.66, our RL, the load resistance here was 1 kilo ohm, and in 1 kilo ohm is like 1,000 ohm. So this is like 1,000 ohm parallel with R out. So it's like 1,000 times R out over 1,000 plus R out is equal to 2.66. If you do some rearrangements out of here, you can find your R out. And your R out is nothing but the same as 2.66 ohm. Yeah, it's because 1,000 is way larger than 2.66. When you have these two parallel together, again, the parallel equivalent will become the same as 2.66. So let me answer to some questions so far. We have Joseph. Joseph, go ahead, please.
Yeah, I was just wondering how we get ROF and RIF. Is it basically the same principle as the
Depends on
resistance reflection rule for the
you see, and if you go back to the lectures, you have different configurations for feedback. You have shunt configuration, series configuration, and each of which has a set of equations for it. For example, what we have here is not shunt, it's series, and then you have your RIF like this equation and ROF like the one in the bottom, the orange bottom. Out after you find these two equations, you should find R in and R out by looking at your circuit and figuring out that what is the relation between R in and RIF. How can you find R in out of RIF, and how can you find R out of ROF?
Okay, thank you.
You're welcome. Aiden, go ahead, please.
Just a quick question. So I noticed, is this considered using a series shunt then for the type of feedback loop?
I should check the equations, but you see the question didn't mention anything about being series shunt versus.
I know, but in order to get like the proper R, the R11 and R2 and R2.
I think it was series connection. Just check the series formula because yesterday I was looking at it to find the equations. I think I was checking for series connection, and the professor also approved that. So
okay.
if you want, just check for it and let me know if there's anything.
I thought it was series shunt just because of it looks like you're subtracting because you're using also when you're this will actually I guess lead into my other question. When you're getting the gain here to use for the both for the actual for the actual gain, and then you also have the feedback gain. You're using the entire system gain, or just the system, or just the feedback gain?
No, the entire system gain.
Yeah, you find A, capital A. You see that A which we found here is the total systems gain. And then when you have that A, you will find your feedback like 1 plus A beta. This is your feedback. And then you can find AF, which is closed loop gain. You can find RIF, ROF, and whatever needed.
Okay, and beta actually is just the inverse of the frequency gain, because shouldn't it only be a portion?
Beta is a portion. Okay, beta is it's, let's say, the equivalence of that feedback circuit. You have R1 and R2, right? If you look at it, and if it's like it's giving you the gain of the beta is not actually giving you the gain. It's giving you the equivalent loop feedback loop resistance.
Yeah, it was just because I'm a bit confused of how you're able to do the inverse of the feedback gain.
That's also equation. Where was it? We had this, and this is an equation.
Yeah, I was just wondering where that came from, because I've never seen us be able to just do the inverse, because I've seen the beta as I've always seen the beta as while it'll have basically the inverse units in order to transform it back. Yeah. I've never seen it as actually the inverse of
I think it's example. I'm not sure. I think it's example 11.4 or 11.9. Let me just quickly check.
So this might not always be true then?
It depends on the. It really depends on the. No, sorry. It's always true, but it's better to check for that example one more time. I think it's 11.4 of the textbook. Okay. You will find the conditions of using AF. Guys, we have a lot of more questions. Let me continue, please. So after H, we have part, I think I. Okay, luckily, Professor said that you do not have to work on I because he hasn't taught you yet. So we're going to omit I. But again, I is pretty easy. You have to find the frequency while the closed loop frequency is given. So that's also another conversion plus something times 1 plus A beta. That's also a piece of cake. Also, let's move on to the last part of this question, and then I'm going to ask some more questions. Part J, it says if for some reason A1 drops to its half of its nominal value, what is the percentage of AF changed? Okay, so let's go back here. I would say part J. In part J, okay, yeah. In part J, I know that A1 will drop to its value. So let's assume that A1 will become half of its initial value, which was 928.5, and then it's like A will become 464.25. And this is what we found in part B. Right? So if this is the case, what will happen to AF? Again, AF is like A over 1 plus A beta. So again, 464.25 over 1 plus 464.25 times 0.2. And you will have 4.90, not 947 volt per volt. So this is our new AF, while our previous AF was this guy, was 4.97. So as you see, there is a drop from 4.97 to 4. Actually, there's a change from 4.97 to 4.947. So we want to find how much is this change. So for finding that change, I would say 4.947 minus 4.97 over the initial value, which was 4.97 times 100%.
then you would find that it's negative 0.47%, and it's like you have this much drop in your AF as well. So this much drop in AF, the feedback loop. So luckily, we finally finished question number 1, but it was only question 1. We have 2 more questions to go, and we have a little time left. So if you guys agree, I continue with question 2. So we have question 2 over here. In this question 2, let's say what it's asked. It said the gain mu is a shunt feedback topology. So you see it's the best choice to give it that what type of topology is it, because directly you will go and take advantage of the set of equations. And the network composed of resistor RF. In order to able to use the feedback equations, you should first convert the signal source to Norton representation. So first of all, we're going to work on this part, and we're going to find the Norton representation. Like example 11.9, guys, this is very important, 11.9, please read it. Like example 11.9, if the loop gain is very large, what approximate of closed loop is realized if Rs is given by 2K, and then find Rf is VO to Vs is negative 10. So, okay, let's work on this. First of all, I am gonna change this to a Norton representation. That will be pretty easy. And by the way, because it was shunt equation, so I just brought the set of equations here, you see. Oh, nice, I have this one as well. I just copied it from that example. Just give me some second, let me drop it right here. Oh, I don't have to draw it one more time because, come on. So it's like we found this. I just copied it from example 11.9. So what I did here, I replaced that Vs and Rs with Is and Rs, right? And so everything else is all stays the same. So what is Is here? Is will become Vs over Rs. And listen, guys, in this example, we do not have that RL, so I'm gonna clean it. Do not have RL. This is a little different from example 11.2. Okay, now that we do not have RL, every other thing will be the same as here. Now, if you refer to example 11.4, you will see that, again, beta is given like 1 over AF, which is general, you always use it. But, oh, sorry, since it's connected to the negative terminal, it will be negative 1 over AF. And then the question is saying that the loop, which loop was? The loop gain is very large. What is the loop gain? Loop gain is A beta. It says if A beta is very, very large, then what's happening? Then it says find AF. So literally we know that AF is A over 1 plus A beta. And on the other hand, do you remember these 2 equations? Let me write them down. AF is VO. These are the equations. Okay, so I'm not deriving it. I'm just using it. AF is always VO over IS. A is VO over II. Remember these equations? So it's like, now that I have the Norton equation, Norton representation, is my AF, continue, my AF will become VO over IS. The source current and the voltage as the VO over it. And what is VO over IS? Guys, you know that IS will follow through here. It will follow through here. And then it will not enter the terminals of amplifiers, so it will just thoroughly enter RF. So it means VO over IS, which was, you can also claim it as to be 1 over beta. Actually, it was negative 1 over beta. Is the same as negative RF. It's like we are finding, using the Ohm law, we are finding the resistance from VO over IS. Now, the question is asking to find the voltage gain. Voltage gain is what is VO versus VS. So you know that you can say VS from this equation over here. You can say VS is RS times IS. So I'm going to replace it. Instead of VS, I'm going to say RSIS, and VO is still the same. So from VO over IS, I know that VO over IS is my AF. So it's like my voltage gain will be AF over RS. And what was AF? AF was that negative RF. So finally, negative RF over RS. And if the question says if RS is 2K, so finally VO over VS will become, and in the, also the question says if the gain is negative 10, so it's like this is negative 10, you have negative RF over 2K. So out of here, RF will end up being 20K, 20 kilo ohm. This is your feedback resistance. So that was all related to part A of the question. Now, part B says, if the amplifier mu has a gain of this much, and input resistance of this much, output resistance of this much, find the actual VO versus VS realized. Now, previously mu wasn't given to us, okay? And now here we also have mu. Remember, from example 11.9, you will have these three equations. Equation number 1, 2, and 3 for shunt configuration. Okay, in this shunt configuration, you have your A, your open circuit gain to be like this. You have your RI like this, and you have your RO like this. So I'm just going to use the equations. I'm not going to do any magic. The question says mu is 10 to the power of 3 volts. And so let's say, first of all, we should find VO versus VS, and then find R in and R out. It says you may use the derived equations from 11.9. And I copied these things from example 11.9. Just for ease of simplifications, ease of the rest. So what would I say here? I would say, first of all, as I find beta, I can simplify. You remember that we said AF is 1 over beta, and then we found 1 over beta to be negative RF. So you can, out of here, you can say that now beta is also 1 over RF. And if beta is 1 over RF, then you will have negative 0.05 milliampere per volt. Now, if you use equation number 2, I mean this equation, RI equation, So from equation 2, what is Ri in this question? Ri will be RID, means input resistance of the amplifier. RF and parallel with RS. These three are parallel together. So it's like 100K parallel with 2K, 20K parallel with 2K. If you calculate it, you see parallel of the resistance will be something pretty much close to the smallest resistance, which is 2K. And if you find it accurately, you will find this much for your Ri. So this is your Ri. The question was asking to find Ri. And now I need to find my, okay. I also need to find Ro. So from equation 3, let's find Ro. Guys, Ro will be that output resistance of the amplifier parallel with RF. But in this case, I do not have load resistance. So because RL is infinity, so we do not have it, it will only be RO, little RO, parallel with RF. So the little RO was given here. It is 2K. So it's like 2K parallel with RF, which was 20K. And I think I do not have the answer here. It's like 2 times 20 over 22. Find it. It would be 1.81 kilo. So this is also the output, RO, according to equation number 3. Now, our next job is to find, according to equation number 1, find the closed loop gain. A is VO over II, and we can use this equation for it directly. Just remember that in this equation, because here we do not have any load in the output, and the load is infinity, you do not have to consider load. The rest is all the same. So for equation 3, oh, sorry, equation 1, I will have A to be mu, which is negative 10 to the power of 3, Ri, which we found it here, 1.78, times RF, which is 20, over that little RO, which is 2, plus 20. Finally, you will have negative 1623.6 kilo ohm. This is your gain. And you remember your gain was VO over II. So this is your open loop gain. Again, for finding the closed loop gain, for shunt configuration is still the same. You will have to do A over 1 plus A beta. So which is 1 plus, it will be negative 1623.6 over 1 plus A times beta, which we found it to be negative 0.05. Calculating it all, and you will have negative 19.76. Okay, so that's also your AF, and the question was still asking for the voltage gain, I mean VO over VS. So again, for finding VO over VS, you would replace VS with RSIS. So you will have VO over RSIS. And remember that VO over IS is the same as AF. Let me scroll up. You see, guys, here, VO over IS is the same as AF. So it's like that part is AF over RS. And you just found your AF. Your AF is that negative 19.76. Your RS is 2. Finally, negative 9.88 is the voltage gain of VO over VS. And that's it. Ooh, lots of work. So remember, oh God, you still need to work on some other part. Guys, sorry that I didn't finish this. We found RI and we found RO, right? But actually, the question is asking about, let's go up. The question is asking about finding R in and R out, not RI and RO. We have to continue this. So let me continue in the next page. Great, you see how beautifully I bring this here? So we do not have part element. Okay, so we've just found that RO is how much? 1.81 and RI was 1.78. So they are RO and RI. What we need to find is R in and R out. First of all, from RO, I'm going to find RO feedback. RO feedback is like what? It's like here. This is ROF. Okay? And guys, if you pay attention, that ROF is the same as where R out is supposed to be because we do not have any load here. So it's like ROF is equal to R out. Whatever you find for ROF, that's just equal to R out. And we know that ROF, let me use another color. In shunt connection, ROF is RO over 1 plus beta. And then it will be like RO 1.81. Oh, sorry. Yeah, over 82. 1 plus 80. 1 beta will also be 82.18. So I'm just directly using it. It will go like 22.1. This is ROF. Now let's find RIF. I'm gonna take some space here. RIF. So what about RIF? According to Shanshani configuration, RIF will be RI over 1 plus A beta. This is all depends on what is the configuration. So RI, we found it previously, it was 1.78 over 82.18. Dividing it and you get 21.7 ohms. On the other hand, so let's see, your RIF is, by the way, if you wanna, it's like you have this. How to show it? Here, you see RIN, guys. RIN is here. This is RIN, and this is our RIF. RIF is before RS. This is RIF is also here. While if you want to find your RIN, it is right before RF. It means your RIN is here. So simply you can say that RIF is like your RS is parallel with RN. see from here, you're seeing Rin, and that thing is parallel with Rs to make RIF. So let me write it down here. I know that for making RIF, I have to parallel Rs with Rin. So I didn't use any formula, I just divided it. I just figured it out myself. Then RIF, we just found it to be 21.7. 21.7 is like parallel with, and remember, Rs was 2K or 2000 ohm, parallel with Rin. And my job is to find Rin. So again, if you do some simple simplifying, your Rin will become almost 21.7 ohm. And this is your Rin, while your R out from here was directly the same as 22.1 ohm. I think finally we're all done. Yeah, finally. Okay, that was it for question number 2. You see, it's pretty long, and we still have one more question to go. I'm afraid that we're not gonna get enough time to finish it, but I will continue as much as I can. So let's move on to question number 3. For question number 3, the amplifier is given like this, and it says Vs has a zero DC component. Fine. So when it says 0 DC component, what does that mean? And then this is not a DC, this is an AC component. And then let's move on to the next part. Find the DC voltages at all nodes and the DC emitter currents. So first of all, we will find the voltage of all nodes. We will find IC1 and IC2. Beta is 100, feedback and V base emitter is given, and then we will find out about VOS and RN. So let's first do some DC analysis. Okay, guys, for DC analysis, as you all know, I will shot this voltage source because it's an AC voltage source. If you shot it, it will be just RS will be directly connected to the ground. Now, let's look at it. First of all, beta is 100. I know that beta is a pretty large number. When beta is 100, we usually assume that IB will be IC over almost 1 plus beta. So IB is almost negligible compared to IC. Make sense? Now, how am I going to begin? I'm going to begin from this current source up there. I know that the current source is entering this node. It will branch out to IB, IB2, and IC1. For now, let's assume that IB2 is what? Let's assume that I can do some easy work here. Let's assume that IB2 is pretty negligible, but still, let's divide that 200 milliampere in both. If you write the KCL in this node, IB2 will become 100 microampere, and IC1 will also become 100 microampere. Okay. Then you have your IC1. IC1 is 100 microampere or 0.1 milliampere. Yep. So you just found your IC1. You have to continue to find your IC2 as well. Okay, now what's happening? Guys, we have a positive and negative 0.7 here. So it's like this point is 0.7. if that point is 0.7, here is also 0.7. And what is happening? There is an I base 1. If you want to write a KCL, there is I base 1 getting out of this node while there is a current, let's say IRS, and this is I feedback. These two are entering. So if I will write a KCL, then name this node A. At node A, you can say that IF is entering the node while IB1 and I'm gonna name it IRS. IRS are exiting the node. And by the way, for finding IB1, then you have your IC1. IB1 is going to be IC1 divided by almost 100. So let's say 101. Then IB1 will become 2 times 10 to the power of negative 6 ampere. Or let's say, you can say 2 times 10 to the power of negative 3 milliamp. This is your IB1. Okay, by putting it here, you have your IB1. And just give me a second, I'm thinking. Okay, it's pretty easy. You can also find your IRS. You can also find the current passing through RS. That's simple. For finding IRS, you would say that the voltage is 0.7 over 10K. And then finally, you will have 0.07 milliampere. So this is also the current passing through RS. If you use it into this KVL, IB1 is 2 times 10 to the power of negative 3 milliampere plus this much milliampere, and finally you will have 0.072 milliampere. This is your I feedback. The feedback loop will have this much current. And now let's find VE2. So you know that this point is VE2, right? How can I find VE2? If you simply write a KVL in this loop, you will find VE2. So after KVL, you would say that VE2 is 0.7 plus RFIF. If you calculate it all, you will have 1.42 volt for your VE2. If you have VE2, you can find V base 2. So V base 2, again, will be, if you write a KVL, there will be VE2 plus a V base emitter. So it's like 1.42 plus 0.7, and you will have 2.12 volt. This is V base 2. If you have V base 2 is connected to the collector of Q1. So V base 2 is equal to VC1, and that's also 2.12 volts. Now that you have all the nodes voltages, let's work on finding IE or IC in Q2. Guys, if VE2, this point, let me write it here. If VE2 is 1.42 volts and RE is 140 ohm, let's find IE2, by the way, which will be 1.42 over 140. You will have almost 10.143 milliampere. You know that because as you have your IE2, IC2 will be beta over beta plus 1 times IE2. They're pretty close. They're like almost the same as IE2. And finally, you will have 10.1215 milliampere for your IC2. And that's it. We found it. So we found the currents, we found the voltages, but it's almost a premise off. And I think we're going to continue this next session. So if anyone has any question, I'll be in